In this video, we are going to go through YJC 2010 Paper 2 Question 4 Part 3. This is a question on the relationship between three planes. So I'm going to start with a summary of three planes. So when we have three planes, the relationship between three planes, there are three cases. The first case is where there is no intersection between the three planes at all. The second case is that there is only one intersection. And the last case is when there is infinitely many number of intersections, in which case it is a line of intersection. For the case where there is no intersection, there are three cases. The first case is when all three planes are parallel. The second case is when two planes are parallel. And the last case is when none of the plane is parallel and we end up with this thing called a triangular prism. When we study the relationship between three planes, once we know that two planes intersect along a line, then we will be interested to look at how that line is related with respect to the third plane. So for instance, the line of intersection, the equation of this line is given by A plus lambda D, whereas for the third plane, the equation is given by R dot N3 equals to big D. So for the three planes to have no intersection at all, we need the line of intersection, which actually contains all the points, all the common points between the first two planes, to not intersect the third plane at all. In order for this to hold true, we need, first of all, D dot N3 is equals to 0. Reason, because if the line of intersection is parallel to the plane, then the direction vector of the line has to be perpendicular to the normal vector of the plane. But when the line is parallel to the third plane, there's a chance that the entire line of intersection lies inside the third plane. And to prevent this from happening, we just need one point on the line to not be lying inside the plane. So we need A dot N3 not equals to D. On the other hand, if we want to have infinitely many number of intersections, then again we want the line, the direction vector of the line dot with the normal vector of the plane to be 0, so that the line is parallel to the plane. But now I want the line to be lying inside the plane, so we need A dot N3 to be equals to D. Okay, in the last case, if we just want there to be a point of intersection between the three planes, then all that we need is that the direction vector of the line is not perpendicular to the normal vector of the plane, in which case my line will just intersect the plane at one point. If you are still unclear about this, I suggest you draw out some diagrams or you look for tutors for clarification, but I just want to emphasize that these conditions over here, you need to know them by heart, because when it comes to solving questions regarding three planes, you will need to use them. So for instance, for this question, I'm told that all three planes P1, P3 and P4 intersect along the line L, which has been found in part 2. And I'm supposed to find the values of lambda and mu. So this is a very typical question for three planes where we have some unknowns. So now we know that P4, the equation of P4 in scalar product form is R dot 5, 1 lambda is equals to mu. The equation of the line of intersection by R is equals to 7 over 4, 9 over 4, 0, plus T174, and this has been found in part 2. If you look at the earlier condition to have infinitely many number of intersections between three planes, these are the two conditions that need to be satisfied, and these are the conditions which we are going to use for this particular question, because we want P1, P3 and P4 to intersect along the line L. So for P4 to also contain the line, of intersection between P1 and P3, basically we need 174, the D, dot with phi 1 lambda to be equals to 0. This will gives us 5 plus 7 plus 4 lambda equals to 0, and we will then find that my lambda is equals to -3. This ensures that the line is parallel to P4, but now for P4 to actually contain the line, we also need one point on the line to satisfy the equation of the plane. So I need this thing over here, dot with my 5, 1 lambda, in this case lambda is -3, to be equals to mu. Okay, and if you solve for this, you will find that your mu is equals to 11. In part B, I'm supposed to deduce the geometrical relationship of the three planes if lambda is -3 and mu is not equals to 11. So for part B, if lambda is equals to -3, the direction vector of the line dot with n4 is equals to 0, which implies that the line of intersection between P1 and P3 is parallel to P4. However, since mu is no longer equals to 11, this means that the line of intersection is not contained in P4. So therefore we get a case where, that the three planes do not intersect, and since all three of them are not parallel to each other, we have a triangular prism. So the important thing for this question that I want to emphasize is the above, that when you study the relationship between three planes, as long as I know two planes intersect along a line, then I'm going to forget about the equations of the two planes. I'm just going to focus on that line of intersection because it contains all the points common to the first two planes, and I'm going to see how that line is related to the third plane.